Today we're going to discuss Chapter 2, Section 4, which is Applications of Linear Equations and Modeling. So a mathematical model is a formula or equation that represents a relationship between two or more variables in a real-world application. So we're going to start dealing with some applications, and we'll do some regression equations using the calculator in the next day or two. Let's start with the first example. Buffalo, New York had 2 feet of snow on the ground before a snowstorm started. During the storm, snow fell at an average rate of 5/8 of an inch per hour. And our job is to write a linear equation to compute the total snow depth, y, after x hours of the storm. Okay, then we're going to graph the equation, and then we're going to use it to find the snow depth after 8 hours, and then we're also going to use it to determine how long the storm lasted if the total snow depth was 31.5 at the end. Okay, so let's start with the first, which is to write a linear equation to compute the total snow depth y after x hours of a storm. Okay, so we have A, and it's y is our snow depth as a function of x, and we know we're getting 5/8, that's our constant rate of change, also known as the slope. And we know that we started with 24 inches on the ground already. Okay. We could also represent this in function notation, which we're going to start to talk about in the next couple of days, as f of x or s of x, snowfall as a function of the rate per hour. Okay. And next we have B, which is going to be our graph. So we'll go ahead and do that. So in this particular case, we don't need any negative values, so we're going to just offset our axes here. And we'll label them according to what information that we have. So I'm going to count by 2s. Okay, and on this side I'm gonna go by 4s so that I can fit what I need to on here. Okay, we're gonna start with our y-intercept, which was 24. So we'll start right here, and then we'll go ahead and calculate the slope, which is 5/8. And so we're going to go up 5, and so that would be 4 would bring us 1, and then I'm going to go up 1 more, so that's up 5, and then over 2, 4, 6, 8. So up 5 over 8, and then I can do that same thing, and that'll bring me up 5 from essentially 29, so that'll bring me up to 34. That'll bring us up to about here, and then we're going to go over 8. And so we have the graph right there. And then next part C is asking us to use our equation that we found in A to compute the depth of the snow after 8 hours. So that means y is the depth equals 5/8. It was for 8 hours of snowfall, and then plus our original amount. So we can go ahead and simplify. So 8 goes into 8, that's 1 time. And so we have 5 plus 24, or 29 inches. So 29 inches. After 8 hours. Now that's including the original 24. Okay, and then lastly, part D, we are looking for the length of the storm duration, given that there's 31.5 inches. So Y represents our height of the snow or snow depth. And then we're going to go ahead and solve that in this case for x, because x represents the duration or the hours of snow. Okay, so we'll use inverse operations to isolate the x. 31.5 minus 24 gives us 7.5. Okay, and then we can go ahead and divide by 5/8. Or you could, of course, multiply by the reciprocal 8/5. Okay, but since we have the calculator, we can go ahead and put in exactly what we have, 7.5 divided by, and then just be careful, you're going to be dividing it by that fraction, so you want to make sure you're entering it carefully, otherwise it might not calculate exactly what we're looking for. And so we get an answer of 12, and you can see that it's incorrect notation, the 7.5 divided by 5/8, so you want to be cautious about that. Okay, and so we have that x equals 12. You also want to make sure that your answer makes sense. It does make sense that a storm could last for 12 hours. Especially in that area when they have lake effect snows. Okay, let's go ahead and do another example, which is, again, word problems. We're talking about applications here. And so in this particular example, we are talking about minimum wage and the hourly wage, or the minimum hourly wage, Y, in dollars per hour in the United States since 1970, can be approximated by the equation Y equals 0.14x plus 1.6, where x represents number of years since 1970, and so that's important information. And so we're saying x equals 0 corresponds to the year 1970, x equals 1 is 1971, and so forth. Okay, the first question asks you to determine the slope of the line, and this is familiar. We've been doing this for quite some time. So the slope of the line is the value in front of x, so in this case 0.14. And it asks you to determine the meaning in this context, okay? So in this case, we would say, since it's referring to minimum wage, we would say the average hourly minimum wage, or minimum hourly wage, and essentially what we're saying is that the minimum wage rose about 14 cents per year since 1970. That's 0.14, so 14 cents per year. Okay, it asks us to find the y-intercept, and in this case the y-intercept would be that $1.60 in this context. And so what do we think that means in the context? Well, that's probably minimum wage in 1970. We're going to say that it's about $1.60, right? Because that's when this equation is approximated for. Okay, starting in 1970, that would be the initial value, so that was our minimum wage at that time. Okay, I'm going to ask you to complete the next two on your own so that we can discuss them tomorrow. It asks you to, it kind of walks you through the process and then asks a couple questions. So I'd like you to do C and D.